I'm going to show a solution to a problem that I came across last week. I thought it's quite an interesting problem and I thought you might be interested to know how it's done too. It's beyond the A-level specification, but I'll try to make things clear so that you understand what's happening even if the equations are new and perhaps the techniques are new as well. So the problem is you have a barrel of water filled to the top. At which height above the bottom of the barrel do you shoot the barrel so that the water projected from the hole will reach a maximum range away from the barrel, so a maximum horizontal range? That's the problem. I'll start by drawing a diagram of the situation. This is our barrel here. Let's continue that along. What do we know about the barrel? Well, it's got a height of uppercase H and it's got a radius of R, and we're going to shoot it above the ground, a height lowercase h. Once we've done that, water will be projected outside due to the pressure in the barrel and follow a projectile trajectory to the ground, and the range for that will be equal to x. We can also say that when it exits the barrel, it will be projected with a velocity v. So those are the dimensions of the problem. We also need to make some assumptions so that we can actually work with this problem. First one, we're going to assume that there's no air resistance. That will still give us a good problem. It does in most projectile problems. Even if you were to take into account air resistance, that may affect the magnitude of the maximum range, but it may not change the position. Of course, you can actually factor in air resistance and then work out and see if it gives you a different solution. But for our purposes here, we're going to assume there's no air resistance. We're going to ignore any of the effects of the bullet actually entering the barrel and all the turbulence that it will produce, any air that it enters, it brings into the barrel with it. We're going to ignore that. We will also assume that the water is projected perfectly horizontally when it leaves the barrel. It may not actually if the bullet didn't hit it exactly horizontally, but we'll assume that it does. And even if it weren't, you could also factor that into the problem. But that's one of our assumptions. And there'll be a few other little assumptions to make the Bernoulli equation, which we'll come across in a moment, to make that work. If you think about it intuitively, then actually what you can see happen, what you can imagine happening is that there's a trade-off in this problem between how, if you're the lower down you are, then there is more water pressure in the barrel, and therefore the water will exit the barrel with higher velocities at lower heights. But that needs to be traded off against the higher you are, the longer the flight time you will have, and therefore you can cover, or the water can cover a larger range. So there's a trade-off between that higher pressure giving you higher velocity and the higher height giving you a longer flight time. So that's what we're working with. Now, in order to come to a mathematical solution, we are going to need some equations. So the first one, I've mentioned this, Bernoulli equation, and that says that pressure, that's static pressure by the way, plus the dynamic pressure plus the potential, which is rho g h, is equal to a constant. What that means is that the sum of those three terms, the static, dynamic and potential, at all points in that barrel are always equal to the same value, the same constant term. This is the total pressure. sometimes called P0. So that is the same wherever you look. Now, what we're interested in are two positions in the barrel. The top. Now, at the top, the water has zero velocity. Actually, when the hole is made in the barrel, the height of the surface of the water will start to drop. We're going to neglect that in order to use this equation. And the second position we're interested in is where the hole is. So the static pressure plus the dynamic plus the potential at both of those points will add up to the same constant. And also, the static pressure at both of those points is equal as well. So we can say that P1 is equal to P2. So that's just so, well, that is true, P1 equals P2, but that will help us with the equation as well. Okay, just to give you a bit of an idea of these two terms, this equation is possibly, this equation you can derive from conservation of energy. So this is like a kinetic energy term, and this is like a potential energy term here. Okay, we need to also use some equations. So this equation deals with the water in the barrel, and it will enable us to find a term for an equation for the velocity at the hole. Once it's out of the hole, it becomes a projectile problem. So we need some projectile equations. So, first equation, dealing with the vertical aspect of the motion. S equals ut plus a half at squared. S is equal to lowercase h, that's the height that it's falling through, the vertical height that is. Now that u in the vertical motion, the initial velocity is 0 because it's coming out perfectly horizontally, remember. Plus a half gt squared. I'm just substituting in the value for g as the acceleration because it's a constant acceleration provided by gravity. The range, x, is equal to that velocity there multiplied by the flight time. So x equals vt. We're going to now start with the Bernoulli equation. What our aim is to find an expression for x just in terms of the height and any other dimensions of the barrel. I want you to notice as well that the velocity term here is not going to be affected by the radius of the barrel. There's no radius here, it just purely depends on the height. So this will be a general solution for a barrel of any width or radius, however you want to express that. So back to Bernoulli then, P1 equals P2. What we're going to do now is write down the Bernoulli equation for positions 1 and 2. So P1 plus a half rho V1 squared. Oh, sorry, that should be a rho. Rho GH1 equals P2 plus okay, so P1 equals P2. We can subtract both of those from both, or we can subtract those from the equation. V1 is 0. Remember, I said that it's 0 here, or at least it's very, very small, so it's effectively 0. H1 right there is uppercase H. V2 is the velocity that we're interested in, the velocity which is projected from the hole, and H2 is the height at which we shoot the barrel, so that's what we're interested in. So that term is all 0. So now we get rho GH uppercase H equals half rho V squared plus rho G lowercase h. Each term has a density expression in it. The density is the same at all points in the barrel, so that will cancel out. So we've got two GH terms there, let's group those together. So we get G uppercase H minus lowercase h. Then we'll multiply by the 2 as well, so we get 2 times that is equal to V squared. That is our first equation then from Bernoulli. Let's use our projectile equations now. And they both have a t in there. T is not of interest to us. We're not interested in finding the flight time. We are interested in finding the maximum range. So what we'll do is we'll take x equals vt and rearrange it for t. So x over v is equal to t. And we can substitute that into our other equation. So h will equal a half g times x over v squared. So we've got substituted in there. Let's rearrange this for v squared. If we get a term for, an equation for v squared, then we can make these two equations equal to each other. So v squared will equal a half g x squared divided by h. So we have two equations there that are both equal to each other. So 1 equals equation 2. So 2g h minus lowercase h is equal to gx squared over 2h. We'll rearrange that for x, starting off by finding what x squared is equal to. X squared will equal, the g's will cancel out here, so it will equal 4h, so that's 2 times 2h times h minus lowercase h. That's our expression for x squared. Therefore x is equal to the square root of 4h times, the square root rather, of h minus lowercase h. We can also bring the square root of 4 out, so that's equal to 2 times the square root of lowercase h, h minus h. But that's the bit we're particularly interested in. That's our expression for x. Okay, so we have eliminated t and eliminated v from our equation. We now have our expression for x purely in terms of the height from the ground that we produce the hole and the height of the barrel. In order to find out mathematically where the maximum x is for that equation, what we can do is differentiate the equation. That will give us an expression for the gradient of the equation. And where the gradient is 0, you'll either have a maximum or a minimum. Now, if you wanted to find out mathematically whether it's a maximum or minimum, you can differentiate again to find the second differential and use that to find out if it's a maximum or minimum. But we can skip that part, because if you think about it, it's either going to be a peak or a trough. So are we going to get a maximum x between these points, or between the maximum height and 0, or are we going to get a minimum? Well, we can appreciate that it's going to vary from 0 here, because down the bottom you have 0 flight time, and here you have 0 velocity. So we know that we've got minima here and here, so it's going to get up to a maximum in between. So we can assume that we'll have a maximum. So let's differentiate the equation. We're going to get rid of this. I'll leave that over there. So x, I'll write the equation up here again, I suppose. 2 times the square root of h. I appreciate that the differentiation won't be exactly straightforward, but you can see the full solution then. X is equal to one function of h, this one, 2 times root h, times g of h, this function here. So we're going to differentiate that equation with parts, differentiation by parts. So if fh is 2 root h, then the differential of that is 2 times a half over root h, which is 1 over root h, I think. Yep. And gh is okay. To differentiate this, what we need to do, we deal with the square root, and then we multiply it by the differentiated term inside the square root. So that would be equal to half times 1 over square root of h minus little h times minus 1. So if you differentiate h minus little h, then you're just left with the coefficient of h, which is minus 1. So that's minus 1 over 2 times h minus lowercase h. Okay, I think I've done that correctly. Yeah. To find out what dx by dh is, let's write that down a little bit now. Dx by dh, that's going to be equal to f times g prime plus g times f prime. So fh was 2 root h times this one here, minus 1 into h, plus gh, which is h minus h all square rooted, times f prime, which is 1 over h square rooted. Okay, so we'll just simplify these out. These twos are going to cancel, so we'll get minus root h over h minus h all square rooted, plus h minus h square rooted over square root of lowercase h. And if we make the denominators the same, then we can add those terms up. So we're going to multiply this by the square root of h over the square root of h. That would be equal to h. So if you multiply the square root of h by the square root of h, you get h. So then we get h minus lowercase h. And here, this term we need to multiply by the square root of h minus h over the same term. So then that will leave us with capital H minus lowercase h, h minus h, all over the same denominator. So we have this, we can add our terms up now. We'll get h minus 2 lowercase h over square root of little h times h minus lowercase h. That's our expression then for the differential of x with respect to h. When will this expression be equal to 0, and therefore where will x be maximum? Dx by dh equals 0 when, if this top term is 0, when h minus 2h equals 0, so therefore h H will equal H over 2. I'm sure you can appreciate that what that means is you get a maximum projection of water when this height is half of the total height of the barrel. So if you shoot the barrel at the midpoint, that's where you get a maximum projection of water. And that actually is quite intuitive. You know, you would have thought it'd be around the middle, right? And it happens to be right in the middle with the assumptions that we made. So, yeah, that's where you would get maximum projection. You can actually go further than that and find out, in terms of the dimensions of the barrel, how far the water will go. So, let's see if we can solve for x max. Let's h is equal to h over 2, and x is equal to 2 times square root of little h, capital minus lowercase h. So x max is equal to 2 times the square root of h over 2 times square root of h minus h over 2. But you see, that's h over 2 as well. Square root of h over 2 times the square root of h over 2 is going to give you h over 2. So x max is equal to 2 times h over 2, which equals h. So the maximum projection, or the range of the water, in this case, the maximum would be equal to the height of the barrel. So that just takes it a little bit further along, finding out an actual value. So if you knew the height of the barrel, you know how far the water would go, roughly. And that's the solution to the problem.